Prova. Prova.
Okay, so sorry for the delay. Actually, we are pretty much on time if we consider the 15 minutes plus. Andrea Manzoni is an associate professor at Politecnico di Milano. He got his PhD in Lausanne, but then he studied in several positions in Milan, Lausanne, and Trieste in Sissa. And he is now associate professor in Milano. His interests are mainly in numerical analysis of partial differential equations, and with a particular focus on reduced order methods. And in recent years, he and his group has largely studied also applications of deep learning to these kind of problems. And he's going to give a very interesting seminar on deep learning-based reduced order methods for real-time numerical approximation of PDEs. If you have any questions, I guess you can interact it also. Thank you very much, Andrea. Thanks, Luca.
Così va. Così. Okay, can you hear me? Okay. So thank you very much, of course, for the kind invitation to Luke and to the MaLGa group. I'm going to talk about our, say, 2.5 years experience in using deep learning based methods for, say, getting as much as we can speed up in the solution of partial differential equations. I would like to then reach complex applications. Before starting, say, a brief summary. So since our experience comes from reduced order modeling of PDEs, and in particular parameterized PDEs, I would like to spend a few words about basic, say, strategies like the reduced basis method for parameterized PDEs, like a sort of linear ancestor of the nonlinear techniques I'm going to introduce, and then moving to deep learning based reduced order models and several, depending on time, then extensions, in particular a POD enhanced version of these DLROMs. DLROMs means deep learning based reduced order models, and if time allows, also possible ways to, say, perform, for instance, time extrapolation, so forecasting the solution of a system even if during the training period we haven't observed the behavior of that system. Several applications to parameterized PDEs problems as well. Before starting, some acknowledgements to the main drivers of what I'm going to talk. Stefania, who got his PhD at MOX, and then she's working with me during her postdoc. Nicola, currently PhD student. Federico has just finished his master project. George has just finished his PhD at the Civil Engineering Department. Stefano is a researcher at MOX in numerical analysis and well, and then more senior people here. Some of you, I guess, you know already. Luca, associate professor, and Paolo, full professor. Attilio is full professor of Scienze delle Costruzioni, so mechanical engineering, and then Alfio. Part of this activity was also related to ongoing project within the framework of the IART ERC project coordinated by Alfio Quarteroni at MOX. Now, this is somehow, say, if you go clockwise, a bit the trip we had in the past couple of years. We started by considering cardiac electrophysiology. We moved to structural mechanics, macro, I would say, and then we moved to micro electromechanical systems, and then we approached fluids. I don't have time to go details about all these applications. I would like just to say, tell you the way we have approached these kind of problems by realizing that previous techniques like reduced basis methods were somehow, say, not sufficiently efficient in order to reach real-time solution. We want to solve these problems many times because of the fact that there are parameters that affect those parameters, those problems, sorry. We want to solve them many times because, for instance, in the first case, some electrical conductivities are related with the patient, and then the behavior of the electrical potential on the ventricle can be affected by those parameters. We want to, for instance, consider the flow through an aneurysm regarding, for instance, the impact of the Reynolds number on the vortex pattern that develops within the aneurysm, and so on. So we want to solve problems many times. These are multi-query problems. You can think that on top of this, there are other problems of great interest: uncertainty quantification problems, inverse problems, optimal control problems. So as soon as you need to solve a PDE many times, either because of, say, input that vary, or because you are interested in addressing real-time computations, then sooner or later you realize that traditional high-fidelity full-order models like the finite element method are not, say, rapid enough. There's plenty of contributions within this year. So depending, either you consider physics-based strategies or more data-driven techniques, well, I guess that you are already familiar with some of the words that appear on the slides. Either you can rely on purely, say, data-driven machine learning emulators or physics-informed neural networks, or, say, at the left, say on the left part, say more physics-based, like the reduced basis method, and then something in between. So since we, say, started with the ideas that stemming from the reduced basis methods, but we also, say, relied on neural networks, I decided to sketch a bit these sort of slides. Then depending, say, on the way you train your model, you can, of course, reach different, say, alternatives. In all these cases, either if you consider, say, more traditional strategies, I'm going to spend a few minutes on this, we need to train the reduced order model by using some snapshots, that is to say, some solutions that I need to compute by relying on the full order model, the FOM. So I cannot, say, replace the finite element approximation. I build something upon it. Okay? So I still rely on the full order model to generate data somehow, either to train a traditional linear reduced order model or a nonlinear ROM based, for instance, on deep learning. Either I rely on low-dimensional linear subspaces, then I fall onto the more traditional reduced basis methods, or, as in the case I'm going to address, we want to rely on nonlinear reduced manifolds. We want to, say, compress to reduce the dimensionality of our data that stem from the numerical approximation of PDEs by using deep learning. And then, depending on what you can do or what you would like to do during the testing stage, so each time you have a new parameter value, then you want to solve the PDE once more, either you build, say, a reduced system in the reduced coordinates that is linear or nonlinear, depending on the problem you started from, or you want to evaluate, say, a neural network map, a neural network-based map that has been trained. And in this way, we can reach the very fast computational time during the testing stage. Or you can do several other things. You can rely either on, say, Gaussian processes, or using neural networks to enforce the equations of the problem, and so on. So we will focus on the left part, and in particular, a sort of intro to the basic strategies that, say, we started from in order to then approach nonlinear reduced order models. So the very first, say, set of slides is devoted to the reduced basis method, in particular by relying on the proper orthogonal decomposition, POD, something that can be called either singular value decomposition or principal component analysis or whatever. Karun-Loewe expansion, if you are more related with stochastic problems. We need to enhance efficiency in this case. In reality, some, say, machine learning strategies already appear here because we rely on clustering algorithms to be able to perform, say, a local reduction. A linear problem to warm up. So sooner or later, if you rely either on finite elements or finite volumes, and then you have a linear, stationary, partial differential equations, you end up with a linear system to solve. NH is the dimension of the linear system. NH can be very large, depending on the discretization you have chosen. And this is the problem, the most basic version of the problem we need to solve. For any mu values, mu is a vector of parameters, or a finite dimensional set of parameters that can affect either the matrix at the left-hand side or the source term, the boundary conditions, whatever. You have to face the solution of a linear system like this one. The idea of the reduced basis method is essentially to sample the solution manifold. So within the finite dimensional space VH in which we seek the solution of the full order model, this is a finite element space, for instance, the parametric dependence induces, say, a structure on the solution set. So instead of looking for a set within this space, you might think that the parametric dependence, say, yields a better structure to the solution set, the solution manifold. So if the parameter is one-dimensional, you have this sort of filament, say, in the space. Each point here is the solution of a problem. So the idea of the reduced basis method, that in part is also inherited by the deep learning-based ROMs, is to sample offline this manifold. This means that for each parameter value sample on the manifold, I compute the solution by using the full order model. So finite element computations are still behind this picture. And this is the offline, this is the training stage, okay? Even before, say, considering neural networks. Then, the interesting part is what happens if a new parameter value mu, different from the ones that I have visited offline, comes, and then I want to solve the problem for the new mu. What happens? Well, instead of looking for an approximation on the black manifold, I'm going to look for the solution on the red manifold that, say, lies on the hyperplane in blue, that is spanned by a set of, say, small n, that will be large n in the slide, in the following slide. The red manifold lies in this low-dimensional space. This in the case in which you have a linear low-dimensional subspace with a dimension that is hopefully very small. NH was the dimension of the previous, say, discretization, the full order model. I hope that this dimension n is much smaller than NH. Otherwise, say, I cannot hope for a good speed up. And then I need to, say, enforce a set of n constraints. I have, say, linear combination of n basis functions. I need to enforce n equations. And this is the idea. So I'm looking for an approximation. Sorry if I am, say, a totally discrete guy in the sense that everything has been already discretized. So I find, say, much more intuitive to look at the, say, algebraic counterpart of all the formulations to be, say, faster also. And I hope simpler. So the original solution, the original finite element, say, solution is approximated by a linear combination of a set of basis functions. V is a matrix that allows me to change the basis between the full order and the reduced order space. And now I need to find n components. This will be the vector. So instead of looking for a vector that lives in r to the power nh, now I'm looking for a vector that lives in r to the power n. Okay? How to do that? Well, I can enforce, say, I can enforce that the residual of the equation, what I get if I replace the original solution with the approximation, is orthogonal to the n columns that span the low-dimensional subspace. I need n constraints. I have n basis functions. This is a possible way. This is nothing but a Galerkin projection. And this brings me to a system that is much similar to the original one. The difference is that now the dimension n is much smaller than nh, because n is the number of the basis functions I have. This is the way I can get the new matrix and the new vector. The point is that I don't want to assemble this matrix in this way, because this would still entail the need to, say, perform nh dimensional computations. But if nh is 1 million, I don't want to, for any mu value online, to deal with 1 million by 1 million matrix vector product. Okay, so I need to be even more clever in order to assemble it. But this is, say, in 3 slides, the philosophy, the idea of the reduced basis method. Everything can be generalized also to, say, time-dependent, non-linear, partial differential equations. The idea is pretty much the same. I'm going to build a low-dimensional subspace also in this case that allows me to find this matrix. And this is related with a best rank and approximation because of the usual results in approximation theory. Hyperreduction is another keyword in this field, and behind this box there are all those techniques. I don't go into details here, but all those techniques that allows me to avoid that, say, calculation of the matrix and the vector in the reduced basis problem before by that matrix products. Okay, and then this is the assumption we have made before. The solution is the linear combination of a set of basis functions, also if the problem is time dependent, and then a projection approach allows me to get a ROM. Also in the unsteady nonlinear case, the ROM looks very similar to the FOM. The structure is the same. All those matrices, Mn, An, are obtainable by that, say, matrix product as before. And this nonlinear term deserves, say, a bit more careful, say, treatment. If you are interested to this, I can give you, say, pointers and, say, details. What happens for a problem in cardiac electrophysiology? Well, this is a problem in which an unsteady reaction diffusion partial differential equations has to be solved. This is say a portion of the tissue. This is a very idealized case. And here there are three parameters. This is the so-called Pinwheel experiment. Because you have a planar wave excitation of the tissue, the propagation of these fronts is typical of this kind of nonlinear reaction mechanism. And then you have a second stimulus. Depending on the way this second stimulus is, say, is given, you can play with three parameters. The time interval between the two stimuli, the radius of the region that you are going to, say, to stimulate, or the properties of the tissue. Well, the behavior can be completely different. Okay, you may think that for each, say, a vector of parameters in this space in 3 dimensions, well, you can, say, jump on the different solutions. What I want to do is to observe some of these solutions for selected parameter values during the training stage, compute the solution, put everything into a matrix, compute the SVD of that matrix, and then produce a basis. This is the basis that I'm going to use instead of the typical finite element basis to, say, to generate all the new solutions for the unseen parameter values. Okay, which is the problem? Well, the reduced basis method works, but the point is that the singular value decay, say, is very slow. This means that if I want to reach some precision, and the error that I get, at least on the, say, training data, is related to the singular values that I discard, well, if I want to get, say, sufficient accuracy, well, the dimension of the reduced basis space can be very large. This means that, say, 600 bases are needed if I want to get, say, a sufficiently good reduced order model. These are solutions with a ROM, say, sufficiently fine with respect to the FOM. The point is that, well, the dimension, the reduced basis dimension can be very large, not only because of the need of, say, generating solutions as linear combination, but also on the right-hand side for the sake of hyperreduction. Somehow I need to linearize the nonlinear operator as well if I want to be, say, efficient in their assembling. And also in this case, say, many terms are needed if I want to be, say, sufficiently accurate in, say, in the interpolation of those terms. So the method works even if I am using, say, local reduced basis. I cluster the snapshots into, say, 6 clusters, and this allows me to decrease a bit. Instead of taking, say, 600, I have 200 basis functions, but this is still too much. Because this means that for any new problem, I need to solve a dynamical system of dimension 200. And at each step, I need to perform operations that are still related with a dimension that is order of 10 to the power 3 because of the assembling of the reduced operators. And this is too much. I'm not able to be real time. Yeah, of course. Yeah. These are the singular values related to the solution snapshot. This means that I'm solving the problem of before for some selected parameter values within that 3-dimensional parameter space. I compute the solution of the problem in time, and I put together into a big matrix, say, solution for different times and different parameters. Always numerical solution. Yeah, yeah. This is finite element. So finite elements, I don't have data here, say a mesh that can be made by, say, 20,000 degrees of freedom. So a nonlinear system to be solved at each time step of dimension 20,000 by 20,000. Yeah, but I consider this to be the ground truth because, say, I can always, say, act on my computational mesh to say, first of all, I do not know, say, the exact solution of this problem at all, but I know all, say, the results from, say, approximation in the finite element context that tells me that depending on the, say, how fine I build the mesh, and then I can predict, of course, that the error scales like powers of h being the mesh size. So I can always, say, think that this can be made as precise as I want. $200 against 20,000, okay? Because I'm putting together 200, say, basis functions, and your comment, allows me also to make another, say, distinction. When you play with finite elements, you have local basis functions that are completely, say, unaware of the problem you're going to solve, right? So the usual triangle basis functions and so on. These basis functions are global. They depend on the problem I'm going to solve. So if I change problem or if I change, say, parameterization, well, the reduced basis will change as well. The key point is that the dimension of this basis is much smaller than the other one. This allows me to compress the dimension of the problem I want to solve, okay? The price to pay is that, say, 200 is already, say, a moderate, say, dimension of the reduced order problem, also because to deal with the nonlinear terms, and this would deserve another seminar, say, completely different from this one, the slower the decay of the singular values, say, the higher number of basis functions I need to, say, perform dimensionality reduction. Okay, this is, say, as usual. If I rely on a, say, global basis, almost 1,000 basis functions are required. The point is that I can also incur instability issues. This is what happens, say, at the end of the training period if I want to solve the problem as before with such a space. So even in presence of local reduced basis spaces, and if I have these coherent structures that propagate over time, somehow if I move to hyperbolic, say, instead of, say, coming from elliptic problems, well, the linear superimposition of modes somehow shows some limits. And this is, say, just one of the, I would say, bottlenecks that we wanted to face. The reduced dimension can be potentially not small as desired. 200, 300 bases can be already quite large. Somehow, it allows me to perform reduction, but maybe this does not allow me to perform real-time solutions. Okay, hyper-reduction, so all I need to treat nonlinear terms can easily become very costly and, even more importantly, very intrusive. And this also prevents reduced order models from being efficient. Another thing here, I haven't told you all the story because I am going to solve for the electric potential, that is the unknown that was reported here, but there are also some auxiliary variables because of the ionic variables that are concentration of ions because of the, say, intra-extracellular exchanges within the tissue. This means that if I want to compute the electrical potential performing, say, common reduced order modeling, I need to write down equations for all the variables that I have. If I'm going to approximate Navier-Stokes equations in velocity pressure formulation, no matter whether I'm only interested to velocity, well, I need also to write down equations for pressure, okay? Also in the reduced order model, and this is another limitation. And last but not least, a projection-based ROMs for parameterized problems hardly allow for time extrapolation. To understand what happens, say, for times that are, say, larger than the end of the training period, this is something for which already here, say, projection-based ROMs are not able to do. These are some limitations, and these are the motivations that, at least the first three motivations, what allowed us to, say, motivated us in order to find alternative ways, and in particular deep learning based ROMs. The idea now is to solve still parameterized problems enhancing efficiency by using deep learning algorithms that are trained on a set of full order model solutions. So this means that some of the ideas that we had before are still valid. In particular, we still rely on data coming from the full order model. We need still to solve the full order model sometimes for selected parameter values to collect data. But the way we handle those data is completely different. I'm no longer interested to find a good matrix to represent the change of basis. I'm more, say, interested to look for a nonlinear map that allows me to reduce dimensionality. Okay. So in a couple of slides. So before, what we were looking for was a linear transformation from, say, the full order model word, finite element approximation, into the reduced one. So small n, which is the small dimension in which before we were solving the problem, was somehow obtained by assuming that the solution in the POD case, in the proper orthogonal decomposition, for this reason I call it a linear ROM, because this is a linear transformation. This is a matrix. The trial manifold, somehow the set of all possible solutions for different times and different parameters, well, was generated once, say, I had an idea of how, say, those reduced coordinates evolve in time. So you have n degrees of freedom, and we had a map that was linear. So the map that from the reduced word allowed me to reconstruct the full order solution was linear, a matrix vector product. The reduced dynamics, somehow the problem solved by the reduced vector, was nothing but, say, a reduced version of the original problem. In this case, this was a nonlinear dynamical system of dimension, and that is the reduced dimension. A possible way is to obtain this by projection. Okay. Now the goal becomes to first of all to remove this assumption. So to look for much more general, say, ways to approximate the parameter to solution map. In particular, I want to approximate directly the map that from the parameters and time for time-dependent problems brings me to the solution. This is not the exact solution. This is still the high-fidelity solutions, but since I can make that solution as precise as I want, then this will be my ground truth. Okay. What happens in nonlinear ROMs? Well, I have some maps. Then in a couple of slides, I try to make this a much more, say, I hope clear and, say, built step by step. So now I have a map that allows me to obtain the full order solution coming from the reduced one. This is no longer a matrix. Before here I had a matrix. Okay, this is a nonlinear map. Once I have, say, the reduced degrees of freedom, then by applying this map to the reduced degrees of freedom, I get what is the trial manifold. So the set of all possible solutions for parameter values and times. Okay, so I have a set of small n reduced order degrees of freedom and another map to learn. This is a nonlinear map, no longer a matrix. I need to learn this map, but I have two maps because I cannot rely yet on that projection process. So I need a second parameter dependent map to be learned. That is what happens for the reduced degrees of freedom. Okay, I need to compress information. I need to find a suitable space of latent variables in which, say, to solve the problem, the new problem. Okay, how to do with that? Well, the idea we had, this is not the only option, of course, is a deep learning based ROM. So I have an autoencoder that is convolutional that allows me to compress the information coming from the original high fidelity data into, say, a low dimensional representation. Okay, so the blue part is an autoencoder. Okay, but this is just one of the two blocks that I need. Remember that I want to solve a problem for any new parameter value. So I need a second map that for parameters and time allows me to get, say, a suitable approximation of the, say, low dimensional representation. So that by training this autoencoder, At the very end, so for the testing stage, well, I will discard the encoder, and I will compose a feed-forward neural network that allows me to learn the, say, map from the parameters and this latent representation composed to the decoder to get an approximation UH tilde of the initial solution. So you have two architectures, an autoencoder in blue and say feed-forward neural network in orange, to somehow learn the reduced solution manifold in blue and what before was called the reduced dynamics. How to train it? I train it by, say, putting together into a loss function two terms. A reconstruction loss, that is an error between the original data and their reconstructed version, plus, say, a sort of coherence loss. I want that, say, the low-dimensional representations that comes from the autoencoder is sufficiently close to what the feed-forward neural network finds. Okay? There are two ways of doing this. Either I train both architectures together or separately. We started by considering, say, a global training, so both networks together, and then, say, a two-step, a two-stage procedure in which before we train the autoencoder, and then we train the second, say, smaller network. All the notations and the details, say, can be found in the paper, so I don't want to stay here to denote all the parameters and so on. Of course, each of these networks, say, comes with a huge number of parameters that have to be found by minimizing, say, a suitable loss function. Okay, all the details related with how many layers and which kind of initialization to the, say, optimization algorithm, say, are in the papers. Okay. It works. This is the problem as before. This is the finite element solution. This is the deep learning based reduced order model with latent dimension equal to 3. In this case, we have two parameters plus time. The parameters are related with, say, the diffusion, so the conductivity coefficient somehow, because of the fact that, say, there are differences that are modulated by this function. So you might think that there are, say, obstacles in the domain that are related with, say, regions in which the signal cannot propagate, say, with the physiological velocity, and then you move around the domain that region somehow. Okay. The good news is that with respect to 240 seconds of the finite element solution that, say, relied on 4,000 degrees of freedom, not a big problem to solve. Here we are going to solve a problem with dimension 3 in, say, 1.8 seconds on a CPU and 0.45 seconds on a GPU. Okay, and if we relied instead on POD Galerkin ROMs with different numbers of local bases, well, say below 8 seconds, we could not, say, go. So at least a factor 8 or even more than 8 with respect to the best linear ROM that we had. Okay. A second case, this is a time-dependent case. Also the previous case was time-dependent. A bit more involved is figure of 8 re-entry, so a more involved dynamics. And also in this case, say the gain is with respect to 400 seconds to, say, 15 seconds on a CPU or a couple of seconds on a GPU. In this case, the reduced dimension is 5. So I guess that some questions start to arise. The first question is how to choose the reduced dimension n. That is, say, the amount of latent coordinate that they use in the case of a DL-ROM. And then many other questions. How to design the architectures, how can I expect, say, the error decays, and so on. I don't have time to address all those questions, but at least I have inserted 3 slides, say, trying to address this question, also knowing the interest that some of you have in this field. We move to the steady case, and we move to the case in which we have an autoencoder, so psi prime and psi, the decoder and the encoder, and phi now is these parameters to this latent representation map. So the reduced order model is the composition of these two maps, the blue one and the green one. The encoder will be discarded. And what we have shown, at least for linear elliptic PDEs with a certain, say, degrees of regularity in the parameter to solution map, is that we can somehow bound what is the, say, this dimension, the minimum dimension and min as a function of the number of parameters. So P is the dimension of the parameter vector that was, say, of finite dimension before. If the parameter to solution map is continuous and locally injective, at some point you can hope that at least P degrees of freedom are required, but as soon as you require that the parameter to solution map is Lipschitz, then you can bound by 2P plus 1 the, say, the dimension of the internal block here. And these rely on a nonlinear extension of the Kolmogorov n width. That is, say, the quantity that allows us to, say, assess at which degree our problem can be solved by means of, say, at which degree the solution manifold can be approximated by linear low-dimensional subspace. Yeah. P are the parameters. Say, in this case, you have, say, mu that is in R2. P is equal to 2 in this case, okay? Somehow here, the question was, well, why in presence of 2 parameters you decided to play with 3 dimensions and not, say, 7 or 10? Well, here the heuristic was, say, P plus 1. P is the number of parameters plus 1 because of the time coordinate we have. At the beginning, say, a couple of years ago, we were not, say, we could not rely on, say, rigorous results. Later came the analysis on this, for the time being, stationary version. If the parameter space is compact and you are facing a second order elliptic PDEs and the coefficients in the PDEs are at least mu-Lipschitz, well, at 2P plus 1 is the maximum that you can play with. And if, moreover, you have a parameter to solution map that is injective, well, P is the dimension to play with. And if you're interested into the details, say, we have an archive preprint for a paper that is currently under review on this. There's something more. Can we, say, bound the error? So the approximation error that is committed by this deep learning-based ROM, well, over the parameter space, I can consider it as the supremum between the, say, solution minus, say, the reduced order solution. I can, say, bound this by putting together 2 different contributions. This is a sort of reconstruction error. U mu is the ground through solution. This is the only action of the autoencoder. Psi prime were the decoder and the encoder, plus the parametric error. This is the error, say, between the output of the small phi map and, say, the encoded version of the solution. And surprisingly, say, the linear Kolmogorov n width comes into play again. We can bound the model complexity, somehow, say, how many weights and how many layers we need for the 2 networks in terms of the accuracy epsilon that we want to reach onto the global error. And M is somehow related with the minimum dimension that is required to have the linear Kolmogorov n width. So this somehow shows a sort of reminiscence of what happened into the, say, case of linear ROMs. In the case in which, say, linear ROMs, say, proper orthogonal decomposition, were fine. Also here, we can hope for a very good reduction. So problems for which linear ROMs were causing, say, much more troubles, well, will somehow reflect also into the complexity of the networks. If you're interested to, say, the proofs and then further details, everything will be, say, very soon, say, added to archive, because this is part of the revision process of this work. Comments. So this M, so the minimum value for which the linear Kolmogorov n width is smaller than epsilon, can be thought as an equivalent linear dimension. So this accuracy is roughly equivalent to the optimal one that can be achieved via projections. Okay, so M can be thought as the number of modes into the previous reduced basis approach. Okay, M does not affect the latent dimension. The latent dimension is related to P, the number of parameters. M has an impact on the complexity of the networks. Okay, and the slower these government with decays, the more degrees of freedom in the neural network architectures will be required, and the higher the number of the training snapshots. And on the other hand, if the linear width decays mildly, say somehow a mix of linear and nonlinear reduction might be an interesting choice. This was a conclusion that we saw, say, theoretically. 1 year later, we already tried, say, practically. Because in the following slides, these are the results. This is an advection diffusion problem, 7 parameters, 4 conductivities into those 4 regions, so constant conductivities in the circle, but parameterized, the transport direction, the angle, and the coordinates of a delta, say, source that can move around the domain but not too close to the boundary are the 7 parameters. And here you have the, say, in terms of error or relative error, the comparison between the POD in blue and the training, the dotted line and the testing, say, errors with, for instance, this autoencoder idea in red. POD allows to improve the accuracy, but of course requires more and more degrees of freedom if you think to the POD matrix that needs to be larger and larger. On the other hand, these DL ROMs, allows us to obtain a similar boost by, putting more degrees of freedom into the decoder, but without modifying the latent dimension. The good news is that we can still play with a very small dimension that in this case is equal to 7. So at the very end, 7 is the reduced dimension, and not 428 or 300 as in the POD case to reach the same accuracy. Somehow, if you want to to put together some few ideas on these DL ROMs, so the dimension of this DL ROM, in particular regarding this latent representation, can be kept extremely small. At least for some classes of parameters, we can show that this can be related to the number of parameters of the problem, the number of the components in the parameters vector. We can query the DL ROM at any time. We no longer need to solve a dynamical system till that time, because this map takes TMU. So I can query the system at which T I want. And if I want the solution at the final time, I don't need to solve all the, dynamics till that time. This is another achievement. We can avoid, that expensive hyper-reduction techniques, even if I didn't give you any detail. There's another thing that somehow puzzled us, the dependence on the dimension of these guys. Because the data that these networks need are still related with the dimension of the high fidelity approximation, the ground truth approximation. This can be very large. But if this is very large, well, also the structure of the autoencoder will reflect this. And for this reason, the DL ROM, despite, being very fast at the testing stage, could still entail severe cost during the training stage. Of course, I'm not going to cover all the slides because I'm going a bit slower. How much time still I have? I don't. Okay. So the idea is to move from DL ROM to POD DL ROM, where POD is proper orthogonal decomposition. So POD DL ROMs add to DL ROMs a first moderate dimensionality reduction based on POD. This means that from the original data I have, so snapshots of the solution in time for parameter values, well, I will apply the idea of the convolutional autoencoder and of this feed-forward neural network to the projected version of this data. So before, it's like the first layer of this convolutional autoencoder is, already decided, and these are, a linear dimensionality reduction. This means that at the very end, I will have, a reconstruction error that is related to the projection of the data onto the POD space. And then as soon as I have recovered, say, the approximation of this projection? Well, by multiplying by the POD matrix, I will get the final solution. So now I have another unknown, capital N is the dimension of the POD. This can be very large. The problem that before, with the reduced basis methods, with the POD Galerkin mode, capital N was the only way to reduce, say, the huge dimension NH. And having a dimension capital N of order thousands could be a problem, could be an issue. Now, this is no longer an issue, because even if here I have data that are thousands dimensions, well, the autoencoder will reduce their dimension to something that is very small at the limit, say close to the number of the parameters I have into play. Okay, so in this sense, we are combining ideas from this DL-ROM way of reducing dimensionality and the old, I would say, more traditional linear dimensionality reduction through POD. No longer POD DL-ROM depends on the foam dimension. Well, the data depends, but everything now is reflected on the capital N dimension. This allows us to avoid long training times, and we also play with the suitable pre-training. This means that we are also able to combine, say, different spatial discretization or different physical laws to enhance even more the training of a POD DL-ROM. For instance, we start by considering the law of a linear material, and then we start by, say, training the networks, and then if the snapshot came from a, say, more complex nonlinear material law, then we, say, adapt, say, our training. Some results. This is related with elastodynamics. So now 64 POD modes plus 3, because we have 3 components, and then a dimension that is related, that is equal to 3 for each mode. And this is the foam, and this is the POD DL-ROM, and this is the error. This is the difference between the solution at a given point. And here, so the training can be, say, further reduced, so about 15 minutes to train, say, the networks, even if, say, at testing time, the networks were already quite fast. These are results from cardiac electrophysiology. The dimension still start becoming quite large, so more than 100,000 degrees of freedom. This is an atrium. This is the 4 pulmonary veins, and this is the activation time, means the time at which the signal has reached a given point within the heartbeat. 7 hours are required by finite elements, an isogeometric analysis simulation in this case, to run on a CPU. Once we have computed everything, all these snapshots, the training is about 5 hours, but this allows us to get less than a second to get, say, this for new parameters that are related with, say, the location of the site in which we are going to activate, say, the tissue. So a sort of, say, advanced version of the first example in electrophysiology you saw before. And this is what happens regarding, say, the potential and the error between the finite elements and the POD DL-ROM. And also in this case, testing times are very small, and this is the comparison with respect to the number of POD modes. So even if the dimension, the POD dimension now, say, scales to 1,000, well, this has, say, a very mild impact on the testing time. Results from fluids, 0.1 seconds to get, say, the solution for different Reynolds number in the typical, say, flow past a cylinder benchmark, and also extended, say, to velocity and pressure approximation. If you want also pressure, well, you can train, say, networks that somehow take into account also data coming from the new variable. So somehow each variable can be approximated independently, because no physical constraints appear in the loss. This is a pro, but this could also be a cons. Okay? And this is what happens in a cerebral aneurysm regarding, say, the velocity. So very small errors, and the speed up of order, say, hundreds of thousands with respect to the full order model for a solution that, say, here you have parameters that are related to the inflow, boundary conditions. Here, then you have the blood that flows through this cerebral aneurysm, and then the different, say, flow patterns that reflect on the way, say, this vortex core, say, develop within the aneurysm, and the error is negligible, I would say. All right, extension to fluid structure interaction. There is also a paper on fluids if you're more interested in these applications. And then, say, a few words, not so many words, regarding the way, say, recurrency mechanisms can be added to POD-DL ROMs to, say, perform, to somehow first take into account the temporal evolution. So for the time being, time was another parameter, was not, say, the time variable. So adding, say, structures that somehow take into account, say, recurrence mechanisms that resemble to a time marching numerical solver was the idea to also, say, consider time as time, and in particular to try to advance the solution, say, for larger times than the ones in which I observed the system during the training. So during testing, I want to solve the problem for new parameter values in the future with respect to the time horizon that I have seen during the training. This is the idea. The idea is to somehow replace, say, layers with a sort of LSTM autoencoder to take into account a set of sequential inputs and, say, provide a low-dimensional representation of the entire time sequence as a single vector. But this is just for parameters. And to treat time, I need to be a bit fast now. I need to solve a sequence-to-sequence learning problem because I want to, say, predict, to forecast the solution where I haven't, say, computed during the training for the snapshot evaluation the solution. And another, say, version, this TPOD LSTM ROM, is the second architecture that is coupled to the previous one within a unique mu-T, say, POD-DL ROM, say, that takes into account LSTM architectures. I know I am very fast on this part, but if you are interested in, there are, say, there's a contributions to a workshop to NeoRIPS last December, and, say, another paper that will appear very soon. At the very end, somehow you have a training set, and then you use this data to train two architectures. This is a two-step process that exploits LSTMs, because the first block predicts the solution for parameters that are new parameters that were not seen before, and the T block takes that prediction and extends it, say, forward in time, so that we can reach, say, this allows us to predict what happens for the new parameter, and within, say, a time series predictor, based on this prediction, we allow to, say, to further advance in time this. And this is a quite powerful architecture to perform, say, prediction for new parameter instances and time extrapolation at the same time. Don't have too much time. This is, for instance, what happens in terms, say, of, say, prediction of testing on a new time window. So tilde gray was the training, say, time period, and this is the prediction for a new parameter value against the true solution, the ground truth, and the error somehow cannot, say, that does not, say, blow up in time. And even if you consider very long, say, testing time windows for new parameter instances, in this case, say, you get nice results. This was somehow a periodic case, but also for non-periodic behaviors. So we started with a simpler case, with a three-dimensional Lotka-Volterra system with a, say, a periodic behavior. In this case, of course, we avoid the former POD reduction because we have already a low-dimensional system. What happens in the case in which you want to predict, say, in time, forward in time till 15, if you stop the training till 10, well, the prediction is very good. And this allowed us, for instance, to get prediction, to perform time extrapolation for the Navier-Stokes case as before, by, say, reaching 7 seconds if we observe till 6 seconds, so at least 1 further seconds. Of course, this is much more involved case for different unseen values of the Reynolds number. I stop here. I don't have time to address applications in microelectromechanical systems by leaving some conclusion. In particular, while the use of deep autoencoders is motivated by the need of encoding and decoding, let's say, a high-fidelity approximation of the solution manifold, we provided, say, a sort of theoretical framework to, say, to study, to assess, say, at least for second-order linear elliptic PDEs, the complexity of the architectures and the minimum latent dimension. But I would also say that a linear dimensionality reduction through POD is still, say, very useful, despite, say, a huge computational speed up can be obtained only through deep learning-based nonlinear ROMs. There are several open issues. This is just the beginning of the story, because, say, except for this case of second-order linear elliptic PDEs, the theory has still to be written. So very lot of results need to be shown. First of all, we need to extend the theoretical results we had on the elliptic PDEs to the time-dependent case. You might wonder if we could embed the physical constraints into the DLROM. So far into the loss function, there are still two contributions related with the reconstruction error and this discrepancy at the reduced level. We're say working now currently on this say way of embedding physics in the DLROM setting. We want also to exploit information on the mesh. So far, the convolutional layers do not take into account, say, the structure of the mesh that we have since the beginning because of the ground truth approximation. And we also want to, for sure, say, deepen, say, the theory behind this time extrapolation problem. So it seems to be working, but we want to better understand why. I thank you for your attention. I hope that you find, say, at least part of this, say, presentation inspiring or interesting. These are some recent references. I'm open, glad to answer your questions or to have, say, a longer discussion till this evening. Thank you. Or curiosity or whatever. A good question. Of course, if the need is just to solve one-shot the problem for a given parameter setting, well, it's not worth it to get through this whole story. Okay. For instance, here, just to take an example, here, a single query costs, say, 7 hours. Of course, I need to compute at least, say, a certain number of snapshots, 18. Okay, so 18 snapshots. So 18 times 7 hours. Well, maybe I have several CPUs in parallel, then I can speed up, of course, and some few more hours to train everything. Of course, I need to say, I want this time to be compatible with the practice. Well, if I can give, for instance, the clinical doctor, say, a tool that in less than a second, no matters, say, if it took a couple of days to compute all the training, but if he's happy with 0.3 seconds for any new, say, query of the problem, well, we have reached the goal. This is strongly depending on the problem. This is quite an extreme case. Yeah, of course. Yeah. Suppose that, for instance, I'm going to activate the tissue there, but for whatever reason, the clinical doctor is telling, well, could you understand what happens if you are going to activate the tissue even a bit more in the left, say? Well, for sure, I will start from that network that I have trained already, and I will add, say, few more training data to take into account, say, somehow conditions that will allow me, I hope, to span, say, over possible conditions also at the testing time. The idea of, say, pre-training was already present in this PODDL ROM. Here, for instance, you can start by considering a given model for the constitutive law of the material, and then, say, I modified, say, the law. So I started by training the networks by considering, say, snapshots that maybe were much simpler to obtain, because running, say, the first model with the first constitutive law was simpler than in the second case. Or, for instance, also the parameter space in this case changed, I guess. Yeah, because here I have now a parameter space that is a bit, say, different or larger. So we indeed started, say, to train the final network, say, since the point at which the previous, say, training was stopped, by considering, for instance, new data or data coming from a new constitutive law or for a new, say, parameter region. So somehow this idea of multiple training, or say few training in few steps, is already present. There are no results on these slides, but on the paper, yes, saying which indeed the effect of this pre-training is quite evident. Then, of course, it depends. If the problem changed completely, and I need to span a completely different range of parameters or conditions, well, okay, I can always start from this, but if the scenarios I want to describe are totally different, well, maybe depending on the case, it's better to start from scratch. I don't know. Of course. Yep. Yep. There are, say, recent results also by Siddhartha Mishra, looking at the effect of the sampling of the parameter space according to, say, low discrepancy sequences, Sobel sequences, and so on, against random sampling, showing also what happens in terms of training data and then, say, accuracy or, say, size of the networks, depending on the data. We did something similar in the linear elliptic cases. For the time being, we are not performing a sort of adaptive search in the parameter space, like, say, greedy algorithms or greedy procedures. This would be too costly. This was somehow, say, the origin of the reduced basis method. So if you do not rely on POD, but you can rely on suitable error estimators between, say, the reduced solution computed with the basis function you have obtained till that point and ground truth, if you can bound the error in an inexpensive way, then, of course, greedy procedure to search in the parameter space are a good option. But very often, say, getting error estimators that are residual based is too expensive if the dimension NH is too large. For this reason, say, we haven't so far, say, analyzed, say, I would say quite deeply, say, the effect of the sampling of the parameter space or somehow possible ways to make that procedure adaptive. This could be another direction, of course. Thanks to you.